Hello, everybody. This is your quick overview of assignment number 13, which is a review of linear and exponential models. First, take out your graphing calculator or turn on the emulator, whichever it is, whichever of the two you're using. For this video, I'll use the emulator, and we're going to plug this data in, year in L1, population in L2, exactly as it's shown. It should look something about like this. Ignore the L4 and L5. There's my year in L1. There's my population in L2. Before I go any farther, I might want to graph this. So I'm going to go second stat plot. I see that plot 1 is already turned on, but I might hit enter to go into this. It's on. It's a scatter plot. It graphs L1 versus L2. Remember, if you need to change this, you can just hit the down arrow to scroll down, hit second, and then the number 1 for L2, etc. When I'm all happy with that, I'll do zoom. And then I'll go down here to zoom stat, which will automatically give it a view that matches the window I put into it. This should look familiar. This curve should look familiar based on homework number 11, the smorgasbord of all possible regressions, but we'll get to that. Moving back to the assignment, the next step is to find the equation of a linear model, then an exponential model. I'm going to demonstrate this, the linear piece, then I'll move on. To do the linear model, I'm going to go stat, over to calculate, lin reg ax plus b. My x is L1, that's good. My y is L2, that's good. I'm going to leave this blank. I want to store it to y1 so I can go ahead and graph it as ready. y1 is a variable, so I'm going to go to vars. It's a y variable. I'm in function mode, and there it is. By the way, when you do the exponential, you might want to store it to y2 so you don't delete what you just saved for the linear regression. Now I'll go to calculate, enter. There's my linear regression in mx plus b form. There's m, there's b. The instructions say to round the slope to the nearest 10. That would be 570. And to round the y-intercept to the nearest 1,000. That would be, let's see, 1,085,000, 1,085,000, round to the nearest 1,000. Negative people back in the year 0. Makes sense. Back in the year 0 when the population of San Rafael was negative 1 million people. After that, I'm going to do the same for the exponential model, but I'm not going to demonstrate that here. And now let's move down. Oh, and finally, I'm going to complete this little sentence here. This first blank comes from my linear model. It's one of the numbers I just said, one of the numbers we're seeing right here. If I want to graph it, I can graph it at the same time. Yeah, it doesn't fit the data all that well. While we're here, though, let me demonstrate a really useful feature, which is trace right here. I'm going to click on trace. And what I get as I put the left and right arrow is I get a little cursor that right now is jumping along the points on my graph and telling me each one of the points on my list. But if I hit the down arrow, it's now sliding along the line on my graph. And if I type in something like 1997 and hit enter, it jumps directly to that point and tells me what, according to the model, the population would be. One thing to note about this is if I do 2050, it can't do it because it's off the graph. So then I might want to go to my window, I might want to go to my window, increase the X max to maybe 2100, go back to my graph, and now widen the graph. And now I could do trace, let's see, trace. Why is this not working? I want to, oh, it's thinking. That's why, because it's still thinking. But now I should be able to trace out to 2050 if I want to. All right, back to here. Trace is what I'm going to need to complete these sentences. Trace is what I'm going to need to find the actual population and the prediction of the model for both the linear and exponential. So that'll help me answer these questions here for 1950 and 2020. Moving down to the residuals, we can figure out which of these two models actually fit the data better. Let's again do the residuals for the linear. You can do the residuals for the exponential. So to do the residuals, I'm going to go back to my stats menu. Remember what the residuals are, by the way. The residual is the difference between the actual data point and what the equation predicted it would be. It's this difference. How many people was the equation wrong by? And then by calculating the total of all the amount that the equations were wrong by, I can figure out which of the equations was wrong by less and therefore fit the data better. That allows me to actually compare the linear and the exponential models. So the residuals, there's a different residual for every point, and that makes the residuals a list. So I'm going to go back to stat. And my emulator feels very frozen. If I hit the on arrow, will that break it? Yes, it will. Go back to stat, hit enter for edit. And I'm going to go here to an empty list, L3. And I want to scroll up and hit enter. So this says L3 equals, not L3 1 equals, not item 1 of the list, but the entire list. And I'm going to tell it that L3 is the list of all the residuals. It is a list of residuals, so it's under your list menu, which is above stat. Second, stat to bring up list, and there it is down at the bottom, resid. This will be the residuals for whatever model I've done most recently. So if I just did the exponential model, it's going to be the exponential residuals. You might have to go back and recalculate the linear model again to get new linear residuals for this graph. Enter. And there's my residuals. This tells me the difference between what the actual data point was and what the equation predicted what it would be for each one of the years in question. Now, if I want to have a total for how long, I can see it was very wrong in 1900. It got pretty close in the 30s, 40s, and 50s. It was almost spot on in the year 2000. And pretty good in 2010 as well. Really, really good in 2010. I can see how close each data point was. If I want to get an aggregate total for this, I want to just add them all up. Well, that's one of the things one variable stats will do for me. Stats, calculate one variable stats on the list of residuals, which is L3. Second, the number 3 for L3, calculate. Now their sum is 3 times 10 to the negative 7, or 0.000003, which is virtually 0. But that's because all the positive and all the negative ones cancel them out. To avoid that, what I really want to look at is the sum of the squares. By squaring them all, now they just add up as one big total instead of the positives and negatives canceling, because squaring makes everything positive. So the sum of my squares is 431 million. Now that number is not very interesting by itself. It's not super useful, but I can compare it to the sum of the squares of the residuals for the exponential model. And then it becomes a way to figure out which of the two models is actually fitting the data better. This one has 431 million. I'm going to write that down for the residual. Now I'm going to go back and repeat this entire process, everything I just did, but with an exponential regression. This final part here, there is a regression that fits this much better than linear or exponential. It's one of the ones in assignment 11. It looks like it would fit perfectly. If you look at the summary at the end of assignment 11, it should look like it would be a perfect fit for this one. Choose carefully, choose wisely, follow all those same steps. Writing the equation, the model, I'm going to give you a hint. It's a very messy model. It'll take you a little while to write the equation down, but it'll have a much better sum of the squares. I want to point out the answer key is at the end of this document, way down here. So don't take a look at that until you're all done. Write your answers on a separate sheet of paper, or print this out, write them here, or type them into a Google Doc, submit that to Canvas when you're done. Best of luck.